Bismillahirrahmanirrahim. In this lecture, we will discuss a new topic. That means we have already finished the previous topic regarding the solution of system of linear equation. Also, how to find the root of a non-linear equation. Now we are moving on to new topic, which is how to obtain the numerical solution of a ordinary differential equation. So first of all, I would like to explain you what do you mean by a differential equation. So a differential equation. So what do you mean by differential equation? Okay, so differential equation. So it is an equation. It is an equation with several derivatives of an unknown function. Okay, it is an equation with several derivative of an unknown function, or we can simply say that it is an equation with derivatives. Okay, and why we are talking about ordinary. Okay, the term ordinary refers to it contains only ordinary derivatives. It contains ordinary derivatives. Ordinary derivatives. What do you mean by this ordinary derivatives? Ordinary derivative means it doesn't contain any partial derivatives. There is no partial derivatives. That means there is no partial, partial differentiation and all. So there is no partial derivatives. Okay, no partial derivatives. It contains only ordinary derivatives. For example, we can say there is a differential equation dy by dx which is equal to y, or you can say another, instead of x you can use another variable, dy by dt is equal to y into t. So these are all differential equation, or you can, instead of x you can use t, y, etc. And you can see that here in this equation we will usually, x is an independent variable and here t is also an independent variable in this equation. You can say that this t is an independent variable, and this here it is a dependent, this y is a dependent variable. Okay, and here also y is a dependent variable. So we are considering like that. So I hope that this is clear. So differential equation is an equation. It contains the several derivatives of an unknown function. So if we are considering the general form of the differential equation, so I can write the general form of the differential equation as dy as some function. You can see that this is nth order derivative. So this is representing the nth order derivatives. Okay, nth order derivative. So it is a function of something like, sometimes it may be a function of x, y, then maybe dy by dx, d square y by dx square, and so on. Okay, so this is an nth order differential equation. So the above one is actually representing a nth order differential equation. Okay, so whenever we are talking about differential equation, we will say it is an ordinary differential equation because it doesn't contain any partial derivative. So you may have doubts that where does it arise, and what is the use of these equations. Okay, the differential equations are having different meanings in different contexts. For example, let us consider the some electrical engineering examples. Okay, so let us consider, so we will talk about the some details regarding the differential equation, then only I will be going into the solving part. So first of all, we will see some example. So you know that consider a circuit like this, right? uh, you know there is a resistor, there is an inductor, and there is a voltage source. Let's say this is V of t. Okay, let us consider like this, and we can take a loop here, and we can write the Kirchhoff law, we can write the KVL. So when you write the KVL, let us say this is positive and negative, assume that it is positive and negative. Now when we write the KVL, you can see that it is minus V of t, and the current will be going like this, right? So this is I of t. So it will be something like, if the current moves like this, plus minus, so plus I of t into R, and you know that the voltage across the inductor is, then it is plus L into di of t over dt. Now this is equal to 0, right? So this is a differential equation, this is a ordinary differential equation, and you can see that here t is the time and I of t is the function of time, right? So we can say that this is a independent variable, we can say that this is an independent variable, and this I of t is a dependent variable, right? So what is the physical meaning of this? Because the current is satisfying a particular equation which contain the differential of the current also. You can see that the order of this differential equation, the order of this equation, what is the order of this equation? You can see that it contains only the first order derivative, right? The first order derivative, right? Since it contains only the first order derivative, then it is known as the first order ordinary differential equation. Now what is the solution of this equation? You know this. The solution is nothing but to obtain the current. What is the function? Current. Okay, because the above equation contains the current as well as it contains the differential of the current, right? So from this equation we need to obtain the current I of t, right? So this is nothing but the solution of this equation. And also you can see that it is only the first order, it is a first order equation, and it contains the first order derivatives, right? So the physical meaning, we can say the physical meaning also conveys that this equation also conveys that it contains only the first order. So it is the first order equation. So we can see that there is only one effective energy storing element. Okay, it contains only one energy storing element. So it contains only one energy storing element, right? So you can see that what is that energy storing element? This one energy storing element, it is nothing but your inductor, right? So inductor will store the energy. So this order of this differential equation is also conveying you the fact that it contains only one energy storing element. So let us consider another example which contains two energy storing element. So if there are two energy storing element, then the number of the order of the differential equation will be 2. Let us consider another example. Example 2. That means we are considering a resistor, we are having a inductor, and there is a capacitor. So it is very clear, right? So we are having energy storing elements as a resistor, capacitor, and the inductor. And let us assume that the polarity is like this, V of t, and this is I of t. Now we can take a loop and solve. So by writing the Kirchhoff law, you can see that this is plus, sorry, not plus, so minus V of t minus V of t, then this is plus minus, so plus I of t into R. Now plus minus, you can see that it is plus L into di of t over dt, plus we need to find what is the voltage across this capacitor, and for the capacitor, you know what is the issue. You know the capacitor Q is equal to C into V, so I of t equal to C into dV of t over dt. That means dV of t is equal to 1 over C I of t dt, or I of t dt. So we can say that V of t, it is nothing but integral 0 to t 1 over C I of t dt, right? So this is nothing but, it's basically an integral equation. It contains both integration and I of t dt, right? It is nothing but I of t dt. Now we can take one more derivative for this equation. That means minus V of t plus, okay, so we are going to the differentiate the I of t, okay, with respect to t. So you can see that you can write this equation in another way also. That is minus V of t is equal to di of t, that is R into di of t over dt, plus L into di of t, that means d square I of t over dt, plus, because to remove the integral, you can take one more derivative. That means it is 1 by c into I of t, right? So we removed the integral here. We removed this integral by differentiation, and this become the second order derivative, right? And this become the first order derivative. So this is equal to 0. Now you can see that the order of this ordinary differential equation is 2, and it is directly giving you how many energy storing elements, okay, are there in this system, okay. But you should be very careful. Suppose there are two inductors in parallel, then you have to take the combination of that, so it will be giving only one energy storing element. For example, you can see here there is a resistor is a capacitor, and here there are two inductor, one capacitor, and this is V of t. In this system, the order is equal to 2, not 3. It is because these inductors are in parallel, so it will be considered as only one inductor. So this is, you should be very careful about this. Similarly for the capacitor also. Now what do you mean by the solution of a differential equation? What do you mean by the solution of a differential equation? So let us consider, so what do you mean by the solution of the ordinary differential equation? So let us consider an example. Dy by dx is equal to cosine x. So it is very easy to find the solution for this differential equation. You can say that dy equal to cosine x into dx. So y equal to integral of cosine x dx, that is y equal to sine x plus some constant, right? So this is the solution. So this is nothing but the solution. So when you differentiate this solution, if you differentiate this solution, then you will get the differential equation, right? Isn't it? So the solution actually is giving you a function. So that function, when you differentiate, actually you are getting the differential equation. And this solution, we can say it is a general solution. And why it is general solution? Because there is a constant. According to this constant, the solution will change. So I will plot the solution, then you will understand it in a more clear way. So let us assume that we have the solution like this, okay, and the solution is sine x. For suppose the value of c is equal to 0, then it is sine x, like it will be like this, right? So this is the case when the value of c is 0, right? So this is also a solution, but this is a particular solution. That means a particular solution means this is nothing but a particular solution, okay, because at this point the value of c is equal to 0, okay. Now we will find another solution. So you can get another solution like this. If you put, for example, c equal to 1, you will get another solution. So this is another solution. This is another solution. So you can see that this is another solution. You can see. So this is another solution. Similarly, you can have, this is maybe for c equal to 1, okay. When c equal to 1, this value 0 will be shifted to 1. This is the value 1. Suppose c is equal to minus 1. Then the value, suppose c equal to minus 1, then the value will be shifted down, right? Then that is another solution. Okay. So this is another solution. So there are a lot of solutions. Similarly, like that, you can, for different values of c, you can get a lot of solution. So the set of all this solution, we will call it as general solution. So the set of all this solution, we will call it as the general solution, okay. And for a particular value of c, for example, c equal to 1 or c equal to 0 or c equal to minus 1 or c equal to 2, 3, 4, anything, 1.5, c equal to 0.05, anything, we will call it as the general solution. And the set of all, we will call it as particular solution. And the set of all the solution, we will be calling it as the general solution. And so you can see that there was a function f of x which is equal to sine x plus c, and when you differentiate this function, actually you are getting a differential equation. So the solution is giving you the original function, right? So that is the solution. So solution is giving you the original function. When you differentiate this function, you are getting a differential equation. But this original function may not be unique. There will be maybe according to the constant, there may be different set of function. You can get a lot of function. So the set of all these functions, we will be calling them as the general solution. And if for a particular value of constant c, we will be calling the solution as a particular solution. So we have general solution and particular solution. Now let us consider another example. Okay, so this is we will consider another example. So I will give you more physical meaning of the differential equation. Okay, we will get a more idea regarding the physical meaning of the differential equation. So let us consider, we can consider an example. Dy over dx is equal to 2x. Okay, so what do you mean by dy by dx? Dy by dx is nothing but the rate of change, right? The rate of change, or you can say it is the slope of the curve, right? It is the slope of the curve. Let us plot this function. Okay, so this is giving you, that means this equation is actually giving you the slope is equal to 2x. You can define the slope by using a simple equation which is 2x, right? So there is x and this is y, and we are plotting the and this is dy by dx. You can say this is dy by dx, dy by dx. Okay, we are plotting the differential equation. Now let us consider the point. For example, we are considering the point x is equal to 0, and there is nothing here. It is only a function of x. It contains only x, and there is no y, right? No y. So whatever be the y, so we can have different values. Suppose we are considering a point at x is equal to 0. Then what is the slope at this point? The slope at that point for x is equal to 0, this is x, and the slope you are getting it as slope is equal to 2x. Suppose x is equal to 0, what you are getting? The slope is also is equal to 0. So I can just mark with a small line, okay, just to represent a small line. Okay. Now let us consider when x is equal to 1, x is equal to 0.5, for example, then the slope is equal to 2 into 0.5, which is equal to 1. The slope is 1. Suppose this is the point where x is equal to 1, that is x is equal to 1. At this point you have a slope which is equal to 1, maybe that is 45 degree. You are having something like this. Now at x is equal to 2, when x is equal to 1, you have 2 into 1, which is equal to 2. Then the slope will be more, right? So you are getting something at x is equal to 2, you are getting more slope. Similarly, here also you will get more slope. So the line will be something like this. Similarly, for the negative values, suppose for example x is equal to minus 0.5, then the slope is equal to minus 1. So you are exactly getting something like this. This is the slope, minus 1, right? This is x is equal to minus 1. X is equal to minus, okay, I have made a mistake here. This is x is equal to 0.5. This is x is equal to 1. Maybe this is x is equal to 2. So this is x is equal to minus 0.5. Now at x is equal to minus 1, you are getting more slope, right? And this is irrespective of y, right? So when you draw all the points, suppose if you consider a point, for example, if you consider a point for all x is equal to 0.5, you have the slope here like this. The slope will be same. The slope will be same for any y, because there is no y in the equation, right? And also this one will be same, like this, right? And here when you consider x is equal to 0 for all values, actually you are getting something known as the slope is equal to. So if you are considering the point which are very close to x, the slope is almost 0. When you are considering any points which are close to 0.5, you have a slope which is equal to 1. And if you are considering any points at x irrespective of y, the slope is more, right? Slope is 2. So this is what. Now you can have something like this here, and similarly like here also you can get something like this. you can see that it is giving you some direction, right? So we are calling this is giving you some directions. You can imagine this like the fluid flow, or how the points are moving. Okay, so the points will be moving along this directions. So we will be calling this as direction field, so another name. So the differential equation is also, we can say the differential equations, can also call them as field or direction fields, or we can say it is also giving you the flow of the points, how the points are moving. So differential equation is giving you how the points are moving. Okay, or we can call the differential equation as a flow. Similarly, we can call the differential equation as a field also. Okay, so I hope that you got some idea regarding this differential equation. Okay, now you know why we are conducting this lecture online. It is because of to avoid the spread of coronavirus. So let us see in that context. You know that the coronavirus will be spreading from one person to another person very rapidly. So we can give one example regarding the spread of coronavirus. Okay, also, so we are going to give one example regarding the spread of coronavirus. You know that we have many peoples will be here, right? Okay, for example, these are all the peoples. Okay, let me I need some time to draw this, sorry. Now so let us consider a lot of peoples are there. Okay, suppose one guy got infected. For example, this guy has got infected. Now you know that it will be easily to spread to this person. Okay, and it can be easily spread to the nearby person, maybe here, 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 right? Now whenever these peoples, for example, if this guy got infected, immediately it will spread to another person, it will spread to another person, right? Like this. Okay, then he may be traveling sometimes, this guy may be traveling, and he may reach here, then what will happen? He will give to the nearby peoples, and it will be spreading. So it will be spreading, right? You understood? Suppose what will happen if the two peoples got so what will happen if two peoples got affected initially? Then they can give to more number of persons. So the new cases will arise. The new cases will be depending upon how many present cases are there. Okay, so you can say that the new cases will depend upon how many cases are reported currently, right? If number of cases in the current situation is less, then the spreading also will be less, and if the peoples are moving, then the spreading will be large, right? So what we can say, that means let us assume that the time, how many cases, the time, you can say the time may be 1 hour, the time axis we can consider 2 hour, the third hour, like this 24th hour, that means this is giving you 1 day. Similarly, the next 25th hour, 26th hour, maybe 48 hours will give you 2 days, and so on. This is the time axis. Okay, this is the time axis. Now we can say that suppose at this particular time, if at the beginning, suppose there are 10 cases, and in the second hour it may spread to maybe some 20 cases. Okay, and this may be something, some number, some 80 cases, maybe something like this. It is going on. Suppose at this moment, suppose these peoples are not traveling, we can traveling, or if they are isolated, then we can reduce the spreading, that you know all these things, because a lot of videos are coming nowadays. Now what I am going to say is the rate of change, that is how fast it is growing, that is the rate of change. Let us assume that y is the variable which is denoting the number of cases at a particular time t. For example, here y equal to 10, so this is denoting y at time t equal to 1 hour. Okay, this is the time. So at time t is equal to 1 hour, this is 10 cases. And how many new cases, that is dy by dt, how it is spreading, that means rate of change, how much fast it is spreading, it is directly proportional to how many cases are there now, right? If there are more cases now, the rate of change also will be more. For example, if 10 persons are infected, at the next moment the rate of the possibility of spreading, the rate of change is very high, right? If only one person, if only 5%, this is very high. Okay, if only 5 people are infected, then the rate of change, you can say it is medium, right? Then if only one person is infected, and if we are properly isolating him, then the number of new cases will be very less, right? That means the rate of change is proportional to y. So this is showing proportional. Okay, proportional. So we can write something like this. So the rate of change, so we can say dy by dt is equal to some constant beta into y, right? This is beta into y. Consider the field for this. We know that dy by dx is equal to beta into y. So let us draw this field. Let us see what is happening here. You can see that this is the okay, instead of x, actually we are using the time as the axis. So this is the time, okay, time axis, and this is dy by dx, which is equal to beta into y. Assume that beta is equal to 1 for sake of convenience. Now you can see that, let us assume that for t equal to 0, we have lot of things. This is the axis, right? Y axis, or y axis is nothing but here dy by dx. Okay, now we will find this is nothing but the slope. Okay, so if you take any point on the y axis, the slope will be proportional to the y. Suppose y is low, then the slope will be like this. When you increase the y, the slope will be like this. When you increase the y, the slope will be like this, right? The slope will be like this, like this. So you see here, when I increase the y, the slope is increasing, right? And this is happening irrespective of time, because this doesn't contain time and not related to time. Related to time, you can see there is no, it's not dy by dx, sorry, it's dy by dt, and it is not related to time. So if you see a slope here, the same slope will be here, right? Same thing. This is what the field, right? And here also you can see something This is the direction field for this. And you can see as the y increases, towards this, you can see the slope is also increasing. You can see this is the slope, right? See. So this is the general solution. Actually what we are seeing now, it is the general solution, or we can say this is the direction field for this. You can see similarly like this for a negative. So this is the field. So this is the direction field for this. Now you know that what is happening here, as the time progresses, the solution for this differential equation, it is a well known differential equation, first order differential equation. It is having the solution e power beta t plus c. So this is actually the solution for this equation. You plot the solution. Suppose for c equal to 0, you will be getting the solution like this, right? This is the case where c equal to 0, and this is the curve e power beta t, and assuming beta equal to 1. Now if you want for c equal to 1, you will get another solution. For c equal to 2, you will get another solution. C equal to 3, you will get another solution. This is for c equal to 1, c equal to 2, c equal to 3. So this is the solution, right? Maybe. So this is the solution. So you can see that this is the direction field. Direction field is giving you, this direction field is giving you how the points are moving. Okay, and you can see that how to control, for we are explaining in a context which is related to the coronavirus. You can see can be modeled by using a first order differential equation also. So you can see that how you can reduce the spreading rate. How you can reduce the spreading rate. How to reduce the spreading rate. Spreading rate. To reduce the spreading rate, actually what you have to do, you have to, because you cannot control y, because you can isolate the person. Y is number of persons, so you can isolate the number of person. By isolating the number of person, actually you can reduce the beta. So if you reduce the beta, actually the curve will be like this. The curve will be slowly growing. Okay, if you reduce the beta. If you increase the beta, if you allow the people, if you don't isolate, or if you don't take any preventive measure, what will happen? The beta will increase, and automatically you will get a curve like this, and it will become very unpredictable growth, or higher order, more than first order. So I hope that this is clear to you. See more definitions then of the differential equations, or more details regarding the differential equations, you can refer any textbooks on it, and also many online tutorials are available. However, the main objective of our course is how to solve the differential equation numerically. And so we discussed about the ordinary differential equation, right? Then we are going to find, okay, obtaining the numerical solution. How to obtain the numerical solution? Obtaining the numerical solution is a challenging task. So before that, I will explain to you what do you mean by the initial value problems and final value problems, okay, boundary value problems. Suppose the initial case, suppose when all the conditions are given at one value x and the solution proceeds from that value of x, then we will call it as an initial value problem. So what do you mean by initial value problem? Okay, suppose it is given a equation dy by dx is equal to something like beta into y, as in the previous case. Now, okay, instead of x I am using t because it's good to use t, time. Okay, now at t equal to t0, you have this much number of cases. For example, y equal to y0, and you are starting from y0. Starting from y0, That means you are starting from t equal to t0, you have y equal to y0. Then according to the differential equation, you will find at time t equal to 1 hour how many, it will be y1, right? Similarly, you will be at time that is t1 and this is at t2, you will find what is y2. So similar, you will be approaching, you will be finding y1, y2, y3, etc. by using the initial information, right? The information regarding time t equal to 0 and how much is y, that is y equal to y0 is given. So by giving these two parameters, you are proceeding further, and this kind of problems are known as initial value problems. Initial value problems. Okay, initial value problems. And suppose, then what do you mean by the final value problems? Boundary value problems. Boundary value problems. Okay. So in the boundary value problem, you can, when if the information at different places, for example at t equal to t0, at t equal to t0 it will be given what is the value, at t equal to t0 the value of y is y0. Similarly at t equal to some, for example t5, the value of y equal to y5, etc. are given, right? And from that we will be finding the remaining values, right? And this kind of problems are known as boundary value problems. Okay, now you have seen the analytical example previously, but the problem with the analytical example, for example, you have seen this dy by dx is equal to cosine x, and you know how to find the solution, because dy is equal to cosine x dx, right? Then y equal to sine x plus c. This is the solution, right? So this is the ordinary differential equation and this is the solution for it. However, since the function is cosine x, it was very easy to find the solution. But this is not possible in all the cases. In some cases, it is very difficult to find the analytical solution. So in many cases, it is difficult, right? It is difficult to find the analytical solution. Analytical solution means by using direct integration without any numerical values, we are finding the general solution for the differential equation. And by using the initial values, we can find the constant c. Anyway, it is very difficult to find in many cases. In this above function, it is very easy, but in some cases it will be difficult. So that is why we are going for the solution of the differential equation by using numerical techniques. That is why we use numerical methods in solving differential equation. So you know that the ordinary differential equation contains only the ordinary derivative. So we will be studying the solution of first order differential equation in this course. So the first order differential equation. So we will take the first order ordinary differential equation. Okay. So that means in general form it has dy by dx is some function of x and y, and it is also given y equal to y naught at x equal to some x naught. So this is the general form of the ordinary first order differential equation. So this is the first order ordinary differential equation. We want to find the numerical solution for this. So we can, the general solution of this kind of equation has can be obtained in two forms. The general solution can be obtained by in two ways. Okay, can be obtained in two forms. Okay, two forms, not two ways, it's two forms. How we can obtain? One is the values of y as a power series, in x, because x is the independent variable. So we will get something like a power series, that is, for example, y equal to 1 plus x square plus x cube plus something like this, like a polynomial or a power series, something maybe e power x, y is equal to e power x, like that. So we will be getting the solution in that power series form. Then another, we can say another procedure, we can get it as by using a set of tabulated values, So what do you mean by this? So what is the solution is nothing but what is the, for a value of x, what is a y, okay, and it is given at x naught y is equal to y naught. Now we will find for some values of x what is the value of y, what is the for this value, particular value of x, what is the value of y, right? Like this we will find out. That means a set of tabulated values. So in numerical methods actually we are going to get it as a set of tabulated values. However, the power series or all those things you can get it as in the previous example, as you have seen. You can see here, for example, this is a power series form. You can see y of t is equal to e power beta t. This is a power series form, right? And similarly you have seen something like this one. Okay, the solution of this differential equation y equal to x square plus c. This is the solution. Just integrate it on both sides. You can get y is equal to x square plus c. So you can see here the graph will be like this. Graph will be like this for different values of c. That's what you are getting here. You see each point is changing like this. So that's what you are going to get here, right? That means the direction field is giving you, without solving itself, the direction field is giving you in which direction each point will be tending towards. Okay, so that's what the solution. Now you can get this, that's what we have discussed, that we can get the solution as a set of tabulated values, and this is what we are going to use in numerical solution of ordinary differential equation. Okay, this is what we are going to use it. And we have different methods. So different methods, so we can get the solution in two different ways, that is, one in analytical form and another in a set of tabulated values or in the numerical form. So we have to obtain the solutions in numerical methods. Actually we have two different ways. That is, one is single step methods, and the second one is the step by step or marching methods. Okay, or multi-step, you can say marching methods, step by step or marching methods. So, or you can say the multi-step method. So in single step method, you have been given an equation dy by dx as some function of x, y, and it is also given that y equal to y naught at x is equal to some x naught. So initial value which will be given. Now, for example, this is for x naught, you are having a y naught. Now, in the next step, what you are going to do? You want to move in this direction, or you can move in this direction, you can move in this direction, or you can move in this direction, any direction you can move. But you will be moving and calculating the new point according to the differential equation, according to the function, So how to obtain this? So suppose according to the function, suppose you move in this direction, right? And you obtain a new point which is known as y1. So for some x1 you got a y1. So you will start with x naught and you have the information y naught. This is given. And by using this information you will find for x1 a new value, or the next value. We can say for the next value x1, you will find what is y1. Similarly, for the next value x2, you will find what is y2. So after reaching this point, you can say you reached here. After reaching this point, according to the differential equation, you will find for example x2, what is the value of y2. So you will be moving in this direction. Similarly, so whenever you do this thing, actually what you are getting a solution. So this is giving you a solution, right? So for any xn, you can say for any xn you will find yn. So these are all the tabulated values, and this is, we will call it as single step method. And why we are calling this as single step? Why single step? Because we use x naught and y naught to calculate y1. We are using we can say that okay, we use x naught and y naught to obtain the value of y1, and we will use x1 and y1 to obtain y2. And that is, we are actually considering only the immediate previous one, or we can say that we are using the current one to find the next. So the current values, that means xn and yn, are used to find xn plus 1 and yn plus 1. That's why we are calling this as single step method. Okay, I hope that is very clear, right? That means we are not using anything before. We are using xn plus 1 and yn plus 1 to if we are using xn and yn to obtain xn plus 1 and yn plus 1. So single step method should be very thorough. That means we use xn and yn to obtain xn plus 1 and yn plus 1. This is known as single step method. Now you know what do you mean by step or the multi-step method. Multi-step or step by step methods. We will use not only xn, we will use xn, yn. Similarly, we will use xn minus 1, yn minus 1 maybe. Sometimes we will use xn minus 2, yn minus 2, etc. The previous things to obtain xn plus 1 and yn plus 1. So this is the method. That means we will be using, okay, you can say xn plus 1, or not or, okay, we will be using xn plus 1, we will be using xn, yn, xn minus 1. That means we will be use the current values, the previous values. That means we will be using the current and previous, maybe some previous values, okay, and we will use all these things to obtain xn plus 1 and yn plus 1. okay, this is what, and this is what this is known as the multi-step method, and the other one is the single step method. So I hope that you understood the clear difference between what do you mean by the multi-step method and single step methods.